Okay, so today we're going to go over transformations with common functions. Sometimes common functions are also called basic curves. And in order to do so, that means we need to go over our basic curves or our common functions. This is not the only basic curves or common functions that you need to know. I'm going to add a little bit more to this list. And as I do, the reason why we call them basic curves or common functions is because you need to know how to graph these functions, know their domain range, etc., or at least sketch the graph of the functions without a graphing calculator. So I know that for some of you, you may be looking at these and thinking they're easy, and some other functions you're looking at and you may be looking at them and saying, oh my goodness, they're hard. And maybe even some of them, you're looking at them and saying, what in the world is that? But you should be familiar with each one of these. That is why at this point, for this year of math that you're taking or beyond, you should be familiar with at least the basic curves before we start talking about transformations with them. So if any of these functions are not familiar to you, you must at some point, and hopefully soon, become familiar with them. Okay, so now the ones that I'm adding here are your 6 basic trigonometric functions. And these we'll get to at another time, actually next term of pre-calculus. However, these are also common or basic curves that you need to know. So if you are unfamiliar, what I would say is to grab a graphing calculator and plug it in, see what you're looking at to familiarize yourselves, or even re-familiarize. There's nothing wrong with reviewing and going over something that you already know. So with that being said, let me go through the sketches without the graphing calculator. So I'm going to do my best. Always have an X and Y axes. And so for our first one, we have y equals x, or f of x equals x. And even though we really just need 2 points, I like to put in the origin. It's a nice odd function here. We're going to talk about even odd functions later. Okay, so for a sketch of number 2, you need these 3 points. It's a nice even function. And for number 3, we need these 3 points to sketch its graph. So sometimes there's same points as in other places, but it's a different function because it's a different curve. This is another nice odd function. All right, so I'm going to keep going, and as I do, if I'm going too fast, stop and pause the video. But I'm up to number 4. I'm going to erase all the ink. And so now I'm up to number 4. So talking about like the domain and range, there is obviously a restricted domain. For the square root of x, we discussed that when we talked about domain and range. Okay, so you should be familiar with it. And just for example, the domain is from 0 to infinity, and the range is from 0 to infinity. So this is something to kind of keep in mind as you're going through your functions. Now we're up to number 5. And again, it's like the same kind of points a lot of times, but different kind of shapes are involved. I'm sorry if I'm not hitting every point that I'm plotting. I'm trying. It's very hard on a tablet. I forgot to label the axes. What am I doing? And I should also have this in as well before I plotted any points. What am I doing? I'm going faster than I possibly can. That's what I'm doing. Okay, this is f of x equals 1 over x. It has a horizontal asymptote at y equals 0, and it has a vertical asymptote at x equals 0. And so that's why you only need these 2 points plotted, because I left in or have the dotted or dashed lines for asymptotes. Whenever you're dealing with rational functions, okay, you should always put in your asymptotes before you start plotting points, okay? And that's why this is a sketch. I don't need so many points to get the full curve because my asymptotes do help me. Now, it's not the only one that has asymptotes, okay? Actually, from 6, 7, 8, 9, 10, 11, they all have asymptotes, okay? So pay attention as I start to do those. Okay, so I'm writing down what E is approximately. So it's going to help when we have to label or know where it is in reference. Oops, that's supposed to be 1E, 0, 1. And this horizontal asymptote at y equals 0 helps get our graph for f of x equals e to the x. This is an exponential function with a natural base. This is something you need to be familiar with. So now we're up to number 8. Okay, so what was the horizontal asymptote? These are actually inverses of each other. So what was the horizontal asymptote is now the vertical asymptote. So instead of y equals 0, it's x equals 0. And I put it in as a dotted or dashed line already. And I'm going to put in some other points. Instead of 0, 1 being a point, 1, 0 is a point. Instead of 1e being a point, E, which is about 2.718, 1 is a point. So now, if I connect these, it goes towards the vertical asymptote. Okay, and with these functions, kind of keep track of the domain and the range as you're looking at them. They are kind of switched as you do look at them. The domain here is from -infinity to infinity, but the range here is from -infinity to infinity. That's because these are inverses of each other. The range here is from 0 to infinity, whereas the domain here is from 0 to infinity, and we're not including the 0. All right, we're up to number 9. Let me squeeze that in here. And some of the same points as before, but a different looking curve. Okay, next one. Okay, I actually want to apologize. 9 and 11 don't have asymptotes, but 10 does. So let me draw that out for you. Let's get a new color. Okay. So with 10, we have a horizontal asymptote at y equals 0 and a vertical asymptote at x equals 0. So it's very similar to number 6, except you can see the denominator is not x, it's x squared. So what happens with the points that I'm going to plot, they're only here. So still bounded between the asymptotes, but in different quadrants. So this is 10, and we're up to our last one, number 11. By the way, I should label. There we go. I'm sorry if I missed any of the function labeling, but I am labeling with the number that corresponds with the function. So you should be okay. Oh. So this one, I like to say, it kind of looks like a bird. It's hard to kind of get the right curve there, but you never draw a bird in the sky with like some clouds, although that doesn't look anything as I'm describing. Let me erase that. That's pretty sad. That's the best way to kind of memorize what f of x equals x to 2/3 looks like. So here we have it. Our basic curves or our common functions, however you want to call it. Let's do some transformations with them. Okay, so in order to do transformations with them, I'm going to talk about the different types. There's mainly just two types that we do in other courses such as calculus, and that would be reflections and shifts. We don't call them translations, we call them shifts, and you would identify them as either horizontal shifts or vertical shifts. Okay, the reflections you need to concern yourselves with are ones that are in the x-axis. Okay, and that's where you negate the function itself, like negate y. And reflections in the y-axis, that's where you would negate x. So kind of jot this down, make sure that you have that part. And I shouldn't really be crossing it out, but I'm trying to highlight that you should be right. Again, with the shifts, you should have listed either horizontal shifts or vertical shift. Horizontal shifts either go to left or right. And vertical shifts either go up or down. So I'm going to first start talking about the vertical shifts, because it's just a matter of adding a number outside of where you see x, and downward if you're subtracting a number from wherever you see x. Sometimes what I mean is that you have an absolute value of x or square root of x. It would be on the outside of that. Okay, maybe in the front, maybe on the back end of the expression. We'll see in a minute. And horizontal shifts, it affects where x is. So if x is under the square root and you see you're subtracting a number, that means you're moving it to the right. And if you're adding a number to it, that means you're moving to the left. So I remember seeing this drawn out for me, and it kind of helps. If you look up towards the sun, it's positive. If you look down at the dirt, it's negative. And if you look left, or you read left to right, it's positive and then negative. So I apologize for those that read left to right, or that find dirt very amusing or interesting or fun, especially when you're planting flowers. But this always kind of helped me when I had to describe my shifts. And please make sure you describe as a horizontal shift or vertical shift. Again, with the reflections, negate y or negate x is reflections in the x-axis or y-axis, respectively. Okay, so we're going to do two things here. For number one, we're going to write the equation, and number two, we're going to describe the transformation. But I also want to do the shifts. So for number one, let's say we actually have our function f of x. graphed for us, at least the sketch of its graph. And again, you should really do the asymptotes first. I'm just in the habit for calculus to put that afterwards. Okay. And so what this is saying is we're reflecting this in the y-axis and then shifting it up 2 units. So you can kind of see what's going to happen graphically, okay? We're going to shift it to units up, and we're going to reflect it in the y-axis. It doesn't actually matter which one you do first if you think about it. If I reflect it and then move it up 2 units, I'm getting this point. If I move this point up 2 units and then reflecting it over, I'm still getting this point. Let me put it in a different color, perhaps. So now, it didn't change my vertical asymptote. That is still going to be the same thing, but this is going to change my horizontal asymptote because I'm moving it up 2 units. So my horizontal asymptote would then be here. Okay. So now let's talk about the other point. If I reflect it in the y-axis and then move it up 2 points, it would be over here. Again, if you moved it up 2 and then transferred it over the y-axis, it still would be in the same point. So this is essentially what its graph would look like, okay, for the new equation. So I'm going to give it a new name. This is g of x. But now we actually have to write the equation. So since we're reflecting it in the y-axis, I'm negating x, okay? And then if I'm shifting it up 2 units, I'm adding 2 to the outside of it. So you can see I actually can reverse this process. It does not matter. This is my equation. The negative should always be in the numerator. Okay? And there we have it. That's number 1. So let's do number 2. Okay, so for number 2, it looks like we have the square root of x. Okay, so let's put in our common function for the square root of x. Right, so that's there. Maybe I should label it. Last time I didn't label the common function. But now we want k of x. And you can start plugging in points if you're not sure of the transformation, just so that you can get a good look at what you're working with. So when x is 0, it's radical 2. Now perhaps you don't know exactly where radical 2 is. So let's try a different number. If we plug in 1 for x, we get the square root of 1. That we do know. We can plot here. So 1 is a point. Okay, I'm trying to make that clear because it's a point for our original function as well. If we plug in 2, we get the square root of 0, which is 0. So you may start saying, okay, it's going downwards, so maybe this function is going in the other way, and it is, okay, because the x was negated. And so this is going to be a reflection in the y-axis, all right? When you have to describe that it's going the other way, always talk about the reflections first, because you want to say that it was a reflection in the y-axis. Okay, let me get a different color here, okay, before moving it over. Otherwise, it's a reflection in a different line. So we want to say that f of x equals radical x was reflected in the y-axis. Then, okay, so now we can actually start talking about how it's shifted over. Okay, so we saw it was going the other way. So it looks like, let me erase that. It's a little sloppy. it looks like it was reflected and then shifted over to units. And that's exactly what happens. So let me draw that in there. This is going to be k of x equals radical negative x plus 2. So then shifted, it was to the right, so we want to say it was horizontally shifted. Spelled that wrong, sorry. To the right. Please remember to write that. I said that a couple times in the other slide. And it was 2 units. Okay, so that's the description of our transformation here. Okay. Now, you may be wondering why, if it went 2 units to the right, it was a plus 2 where there is an x. Because in my last slide, I had said, oh, if it's going to the right, it's minus something. That's because it's under the square root, so it's affecting all of where x is. So it's a matter of actually looking at this and saying that you're factoring out the negative. So this is indicating the reflection in the y-axis, and the minus 2 is indicating the shift horizontally to the right. So knowing the curves and knowing the graphs is super important because it can double check your work or your answer. Okay? So hopefully you understood both examples and all your curves. Good luck.